Hello everyone, this is week 9. We will be talking about object-oriented programming. Thus far, the last two videos we've talked about basically simulating and optimization and using them together. Today's topic is a bit off. Um, we will be talking about object-oriented programming, which is a concept that's mostly used and it's also available in MATLAB. And sometimes when you're generating reports, these kind of um, paradigms may help you out here, or it's good to know how to use, object-oriented programming in MATLAB. So it's going to be a different video here. Let's dive into it. Now, the closest thing to an object in MATLAB, as it is in C, is basically struct. So if you remember struct, hopefully it pops up now. If you remember struct, it's basically a packaged data type where you can have some fields and values. For example, you can define a struct, let's say struct. You can say, for example, name, and then give it a name, maybe age, and then give it an age, and stuff like that. So then you have basically the possibility of using a dot operator where you say result.name is basically the name, result.age is basically the age. When you use the symbolic function solve, which we use sometimes, it kind of generates the structure here, so you should be familiar with it. And this is basically the C type that we are familiar with and use most of the time. That's available in MATLAB. There are some interesting functions that we didn't really look at, but you can just read the documentation here, where you can test if there's a field that you're trying to access, or look up the field names, if it's a struct type or not, because you want to have some proper error handling here. So that's basically the closest thing that we can call an object. But the problem with structs, because it's a C type, and in C we don't have object-oriented programming capabilities, um, it doesn't contain the functions. Therefore, the methods of a certain data type of the struct, for example, you cannot embed functions into this. Well, technically, you might add some function pointers, maybe, like maybe function, and then I don't know, maybe x that returns 2 times x. Maybe that's possible, but it's not the proper way where I can say, okay, I'm going to invoke the function here. Let's have 2. In MATLAB, this is kind of possible. In C, you can do that too. You can just embed function pointers somehow. But the proper way is to use the object-oriented programming, the name class here, because we are trying to do probably graphical user interface stuff or some management code where we want to address stuff in our code like objects. When you want to use objects, it becomes a higher level of a programming language, because when you're, for example, using machine code assembly, then you are too close to the hardware, and that language doesn't resemble a human language, and it's not really easy to understand. Whereas C, C++ put on top of that is a more readable one, but still it lacks the human communication, because it's still a programming language. The higher the programming language is, the easier for us it is to understand and code, basically. And here we have some examples where you might want to use object-oriented programming just as a concept. I want to just show you how to define them, what are specific things about it, just an introductory level of object-oriented programming, just one dose, so you can get started with advanced stuff if you're interested in it or if you're needing it. So basically, it is a struct with some functions, but we are not defining it as a struct. As you can see here, MATLAB just says it is a struct. It's not a specific data type. And well, we are not embedding stuff into it. We are not using it properly at this point. Structs are just basically things that you want to pass around and have just a basic understanding. In C, you start out with that, and when your needs become even more, then you might want to opt for a class. Now, what is a class? Well, basically, class has, again, some fields where we have some properties, and those properties can be of any data type. Then we also have methods embedded into it, not like this one here. This is basically just a function pointer. You are just writing the function inside of this class, the whole definition, and then you can use that class, instantiate multiple instances out of it, so you can create objects out of a class, and then you have the properties, the proper functions, and your code becomes cleaner, and hopefully you'll have some differentiation between the things that should stay in a class that shouldn't be accessed or seen outside of it, or things that should be seen from the outside. So basically we are trying to encapsulate our code in a way that if we give it to someone, they can use it easier and they don't really need to know what the internals are. If you're passing the whole C project or MATLAB project and you have just basically dumped in all the code, then it's not really that portable and readable for someone who didn't write the code. So this encapsulation, this layering here with objects may help out a little bit more. So let's dive into the actual example here so that we can basically talk more technically. Um, so let's see. Now, first of all, let's start with the documentation class def. We are defining classes using class def here. Define a new class or subclass. The keyword class def denotes the start of a MATLAB class definition. That's basically what we are going to use. And there's a neat example here. You create, again, in MATLAB, what we do is if we are creating a function, we name the script file using the function name. If we are creating a new class, that's going to be the class name as a script. Now we are going to code a polynomial class that should resemble that should bring up some familiarity here. And then we have this structure here. I'm just going to copy the first part here and just paste it in. There we go. So yeah. Now, of course, our class is not payment. It's going to be polynomial. And then we will have some properties, the methods, and that's basically it. Our very basic class. Now, the thing about this class is that, for example, we might have some coefficients inside of it. Because, yeah, polynomials have coefficients. Now, but it might be the case that I just want to hide these coefficients. So you can have multiple properties blocks here. So let me just, nope. Let me just indent them back. For some reason, my editor doesn't do the job here. So these are the properties. Basically, in a struct, when we are defining the struct, we give the field names. These can be thought of as field names. And then we will write in some functions here. But I can have some private layer where if I define it, the class on its own, the functions given here in methods, can only access that data. So I can have some local data, like a function. You cannot access the local variables of a function outside of it. So we can do that here with a class 2. What we have to do is we have to provide an access private here, so that these are going to be private variables. So I don't want to show the coefs here. So if you call polynom with parentheses, you have a polynomial. So this is the way how we are going to create objects out of a class. So this is the class. This is kind of the template, and we're creating a object out of it, and we're just using it like a function. Now, when we define it, you can see that it has no properties, and the reason for that is access private. What happens if I, for example, comment out this part here and put in a comment here? So it means that we have properties coefs and methods like this. I have to run it twice. Now you can see we have a field or property coefs where we are going to store the coefficients. Now, if you don't want to mess up stuff, and if you, when you deploy, want to hide some stuff inside the class, because if someone touches it from outside, then you might mess up the whole algorithms or functions here, then you might want to need to use access private like this. And you might also have some accessible properties, which you would then list here. Now, in MATLAB, we don't have data types. It is based on the assignment, the kind of R value, the right hand side value. Therefore, we don't need to define anything. This is coefs, and this is basically anything. It could be anything. It could be a string. So let me demonstrate that. So let us define it. So what I can do is I can just go to coefs and maybe assign a string. You can see I didn't actually limit this to a certain data type, but it is possible to do that, and I'm going to do that now. You can just say this is going to be double. Now, when that's the case, let us create it back again and do this assignment. Even though we set double, now instead of having a string like notation or data, we kind of get the ASCII table correspondence here. So it is interesting, but it still works like a double vector here. Now this could be the reason why you want to hide stuff from here. Now this is not a proper way of defining coefficients. I'm not defining 97s squared plus 115s plus 100. I'm trying to assign a certain string to it. So this is sometimes this could be a reason to hide stuff from outside, so it's not accessible, and they have to provide, for example, like a function, they have to provide some arguments, and you set it up for them with some controls, with some checking. So therefore, let's go ahead and open up the access private here, so that we're basically hiding it from the user here. Now, of course, when we're hiding it, what are we going to do at this point? Well, let's actually have a function here. Let me just get rid of the properties for now. Now, in the classes or objects, we have important functions. One of them is called the constructor, and we've already seen it. The constructor here is basically the class name and then parentheses. So here we're creating an object. Therefore, it's called the constructor. So this is basically a function that is the same name as the class, and it is called the constructor here. Now, let me warn you, if you are coming from a background like C++, or maybe Java or C#, then the MATLAB class definitions will not make that much sense for you. If you're coming from Python, for example, then you might be more familiar with the MATLAB way, because they share similarities in object definition and handling, and you will see why in a minute. If you are coming from Python, you're good to go, but if not, try to bear with me, because it can be troublesome for you to understand why we're doing it like this. Well, now let's just define a function, and you can see I'm just defining a function. I'm going to get rid of the internals of my function. And this is not just any function. This is going to be a function with the same name. So I'm basically defining this. Now, if you don't define this function, you can still have that function. It seems like this is basically always there because it's a constructor. If you have a class, an object, then you should always have that creation function, sort of. So the constructor. Now we will have some input, let's say val, and we are going to have some obj. And that's exactly what I mean by that. I use obj. You might use self. This is kind of the Python way of doing stuff. So this is the new object, kind of. So and in C, or actually C++, we have the keyword this. So this is kind of like self, but not quite, because it has some differences. This one is the pointer, but this is the whole thing. So it's not a pointer, and it is used a bit differently. But you can get used to it, I'd say. So let's call it object. And well, this is actually the line that we have here. I call it result or something or object. I can also call it object. This is basically that line. So when we are creating the object, what are we going to do? Well, we can do some checks. For example, we can do if nargen number of arguments in are 0 or is 0, then do some stuff. Else if narg in is equal to 1, do some other stuff. I don't know for some reason. You can also have else. You can also have else and display not supported or something like that, or even a better supported, maybe a better information message here, but that's going to be basically it. Now, let's actually use this polynom class like a symbolic object handler. So what I mean by that is, let's just define symbolic s, for example, sims s, and then have a certain polynomial, s squared plus s plus, I don't know, 1. And let's pass that into the polynomial, into this object here. So I want to use it like this. And of course, the coefficients here should be calculated directly from this, and then maybe handled that way. So if I want to access this property here, this is a property of the object. And I've shown you the struct way. I've shown you that I can just use the dot operator here. That is also available here. So when I'm inside the class definition, I'm going to use obj dot coefs equals 0 in this case. Why did I access it this way? Because I'm returning objects. So this is going to be the created object. And the property that I'm going to return of this object is going to be coefs, and I should divide it 0. So if that's not the thing, because there might be other usages, like I might also want to give it a vector here. So I want to define an object that both accepts symbolic expressions as an input and then stores it like a polynomial, or I might also just give it the vector. It should also again store it like it should do. If I don't provide anything, it should just define a 0 polynomial. If I pass in something else, it should show me an error, so I'm handling everything properly. So if there's nothing, object coefs is going to be 0. What we can do is we can always assign it to 0 first, and then do nothing maybe, or repeat it. And if we have an input, what we need to know at this point is it a double vector? Is it a symbolic variable? So there's something called isa, and you can determine what it is. For example, let's give it a value. Is it a double? It is. Is it a symbolic expression? It's not. So I can use an if statement here and is a, and then give it the value and then check if it's double or not. So let's have else if is a val sim, and then else, and then and. So if it's a double, let's display double to see if it's working. If it's symbolic, let's just show that it is symbolic. If not, let's throw some error. I like to use assertions sometimes. And let's say no constructor. Now, what we can also do is we can ask for the data type using class. So, for example, what is the class of ASD? It's char. What is the class of 12? It's going to be double. What is the class of sim S? Obviously sim. So we can just use class, and you can also do, instead of is a, you can use that one here, but it's more safer to use is a. Basically, I can append um, for type and then just convert it into a string, the class name of the value that we did provide here. So we have a constructor. In this constructor, we are hiding the coefficients from the user. We are defining it equal to 0 if nothing happens. If there's nothing provided, it's a 0 polynomial. If there's an argument, if there's just one argument, we're checking if it's a double, if it's a symbolic one, or else. Now, if it's double, we're displaying double. If it's symbolic, we're displaying sim. If it's not, we are basically throwing an error. At this point, the execution will stop and we will see the error message. No constructor for type string something. So we are going to see that. And more than one or more than one inputs are not basically supported yet. So let me create that polynom. So if it's empty, I have no properties. Well, I'm not seeing what I'm assigning here, but no problem at all. So let's provide 1, 2, 3. You can see double pops up here, so we can see that we are assigning a double. Let's define a sim x, for example. We can see it displayed sim, so we did enter this if, we did enter this one here. Now what happens if I, for example, say true? You can see, I hope the sound was also on the video. You can see that error using polynomial line 16, no constructor for type logical. Now, you might have seen these types of errors if you use assertion, if you use assert here and give it false. If this is true, it will not assert, but if it's false, if it's violated, then it will give some error and it will throw or display the error message here. So that's basically us ensuring that the user provides at least double or symbolic things. And well, we can do the same here. We can also assert here. Not enough. Let's maybe display not enough. Not enough input arguments. Something like this. I don't know, maybe not the best one here. Or actually, too many input arguments, because we have covered 0 and 1. It seems like we have too many of them. So what happens if I, for example, do something like this, too many input arguments? So we are basically protecting ourselves here. Why did it? Interesting. If I provide Oh, now it kind of changed it. Oh yeah, makes sense. So if I try to create it, it says too many arguments. If I do it like it should be done, you can see we're safe. So we are kind of thinking deployment and production, and we are going to give this polynomial class to someone. If they don't touch the internals, if they are just going to use it, they, if we coded it cleanly and if we thought everything out, it should be working as expected. So we're just protecting our code. We're just protecting the user in order to yeah, be able to work with this. Now, I hope that you can see the difference here, and when we go on, it will hopefully become more obvious. But if I would have provided someone just a code that does the checking, where at the beginning you have a polynomial, if you change that, everything throughout down from then on is executed, you might just mess up the whole code if you're not an experienced programmer, for example, or even if you are, if you don't know what you're doing, you're just messing up the code. So this is a way of preventing that. So yeah, I've talked about the fact that if it's a double, I'm just going to basically object dot coefs and then assign it to the value here. So if it's not that, if it's a symbolic expression, what I need to do is I need to basically first find what the variable is, because we can use x, we can use s, we can use anything. So there's a function called Simar and value, and let's look at the documentation here of Simar. It searches for string identifiers, and you can basically find what the unknowns or the symbolic variables are. Now, we hope that there's just one. We will just say simvar val1 and find the symbolic expression here. So let me just execute it here. Let's say sim. So this is basically x squared, but it gives us x. So we know that the symbolic variable is x. Of course, there's a possibility that we have sim and then y, and it gives us the first one here, then there's the second one here, or it just gives us one. If we need two of them, it gives us both of them. So there's we will assume that the user is going to put in just one. If I overcomplicate this example, then I would miss the point here. So um, as you might remember, we have something called coefs, and it works with symbolic variables. Now we have the value, which is going to be the symbolic expression. We need the variable like s, so I'm going to put it in here. And then we call all, because that's the protocol that we always need to think about. Now the problem or the issue here would be the fact that this part here can return symbolic, or will return symbolic data. So I need to convert it into double. So this is what we have done so far. So basically, yeah, that's basically it. Now, yeah, if I execute it, we will not see anything because we've hidden it. So maybe we should just get rid of this part here in order to be able to see what's going on. So let's create our polynomial. You can see we cannot do it. 1, 2, 3. You can see it's 1, 2, 3. Now let's define s and then define s squared plus 2 times s, or 20 times s plus 12. You can see it automatically determined the symbolic variable, and it calculated the coefficients. And even though I've put in another data type, it just converted it into its own data type or storing methods, which is basically the coefficients from high order to low order as doubles. So this is basically the thing that we're looking for. So this class is going to unify using vectors or symbolic variables for polynomials. Of course, it's just an example that I came up with, so it's not really going to be used. But yeah. Now, we will have some properties. We have display, so I'm going to have that capability. But let's have a function is 0 that determines if the polynomial is equal to 0, if the whole polynomial is equal to 0. Now, if we are basically defining another function, so this function, and I guess this and here belongs to each other. So here we can just call function, call it will return value, and it's going to be is 0, and then we are providing object here. So usually, if we are using MATLAB Python, you will provide self here. So that's basically what it is. But in C, we don't really need that. You just provide nothing here. And this confuses the user most of the time. This might also confuse you, but inside the class definition, if we're defining a function, the function here, maybe you have already experienced this. If you have nested functions, you can define a function and then define another function inside of that. Then the function can access the global stuff here in the function. But here we need to provide explicitly the object here in order to be able to handle the class. So except the constructor, because this is the constructor here. So this is the constructor here. If we're not in the constructor, each other function here, like is 0, should have the object handle. The constructor itself returns the object, therefore it doesn't need an argument like that. But if you are going to code another function, add another method here, then you should always have object as the first argument here. And when you're using it, you don't need to have, you don't need to provide this object there. So I'm going to show you in a minute. Now, we are going to look for the following. Now, it can happen that the coefficients here are all 0. And that could happen like this. If we have, for example, s squared, and then if we subtract it from itself, then we will have 3 zeros. So this is going to be a vector, basically, and we are going to check if the whole vector is 0. You cannot just do object dot coef equals 0. That doesn't make sense. Of course, in MATLAB, when you have a vector of zeros, and if you're checking for vector equals 0, it will give you basically the ones that satisfy that. So we can maybe use that and see, well, is it going to be are all the coefficients 0 or not? So I can also do this by using the not operator here, so that if something is not equal to 0, I will see if it's not equal to 0. So let me redefine this. For example, the last one here, if it's not equal to 0, I will get definitely something else than 0. So what I expect ideally is I want to have a vector that stores the indices which are not 0, and the sum of those should be equal to 0. So this way, without using any for loop or while loop, I can ensure that there was no 1 available here. So it's kind of like an OR operation here. If you OR it, you will see it's 1. It's also summation, basically. Yeah, this should actually return that. So let's have val equals this. Now you can see I have assigned it like this, so it means that the value here will be true or false. So let's test it out. So let's have a polynomial res.is 0, You can see I'm not going to provide anything, but yeah, what's the problem here? Oh, it's called coef with coefs actually. I'm sorry. Like this. You can see I'm accessing it with .is0 and it says false. It's not a zero polynomial. If it's a zero polynomial, you can see it returns true. So I can return true or false and check if all the coefficients are basically zero or not. If I'm going to create it like 0 here and check if it's 0, it still works. So I have basically a way of determining if the polynomial is a zero polynomial. So let's have eval, a function that will evaluate the polynomial for some given value. We are going to substitute a value into basically into the polynomial. So function, let's have the return value, and the function is called eval. And then we have the object here. Now, if I'm going to provide a parameter, this is basically a zero argument function. This is going to be a one argument function. The first argument is always object because we need the handle of the object, but then we are basically giving it the actual argument. So this is a hidden argument actually. The object argument is never going to show up in the usage. It's just in the definition here. If you don't provide object, then you don't have the access to object.coefs. So therefore you need it here. And this is also applied in Python. That was what I meant by if you're coming from the background with Python knowledge, then you will just get the whole idea here. So now I want to basically put in some number, px, give x2, and see or find out the return value here. So let's call something pval here. Now I'm going to get the length of the object.coefs here and subtract one, so I have basically the order here. And what I'm going to do is I'm just going to do it using arithmetic, basically, because I know how many coefficients there are. I'm going to get the coefficient object dot coefs I. So I get the coefficient. I'm basically going to add pval plus coefficient times the value to power. Now the highest order term will be n, and I'm going to subtract I because I is increasing, so the order should decrease. But if I is equal to n plus 1, then I have minus 1, so I should basically add 1. So n plus 1 minus I is going to be actually the power here. And the reason for that is if you plug in I equals 1, these two will cancel out and you will have the nth order, which is the highest order term here. So for example, this one here should be power 2, this one should be power 1, and this one should be power 0 here. I could also basically use we could also basically use the substitute function from the symbolic toolbox here, but I'm not relying too much on that, just in case. So you can use substitute, but I'm just going to do it like this. So when we have that, let's actually define a polynomial 1 to 1, I guess. And result.eval, if it's 0, it should be 1. If it's like 2, it should be 4 plus 2 plus 1, or 4 plus 4 plus 1, of course, 9. So it seems to be working here. So minus 1 gives us 0. So we can evaluate the polynomial, which is quite nice actually. So, of course, these two functions can be coded like add some functions called pol underscore is zero, pol underscore eval, and this would all lose its meaning because we're working on vectors. Of course, here I'm trying to make an example that is more suitable for our lecture, but now we want to add two polynomials to each other. We're kind of treating it like an object, and I want to just exemplify that. Of course, this polynomial class is not the best example. Yeah, so let's have plus that adds another polynomial to the current polynomial. So how are we going to do that? Now, this is also going to be a function. And this function is going to return the object. And it will basically be called plus. And then we again have object. And we call it the other. Now this is not no ordinary function. And we'll see why. Now the thing is the following. The thing that I called here other could be a polynomial object, so it could be the object itself, but another instance, or it could be a double. So I'm going to use again if, and this strategy here is if the other is a double, else else if is a now we can also use polynomial as a class name because this is our data type now. Let's have else and end. So what are we going to do if this is basically a double? Now, well, there's this problem where we have basically the possibility of providing a higher order polynomial in the plus operation. So this other plus object. So that's what we are trying to implement here. So let me just write it down here. Object plus other. And all that we store are the coefficients. So we have object.coefs and other.coefs. Now we need to check if, for example, this one is a longer, a bigger vector or equal vector in length than other. If that's the case, we will just sum these two vectors together. But if not, we might pad this one with 0, or vice versa. We will just need some padding for the smaller one. So in order to do that, what we can do is we can just have a, for example, sort of a distance and see if the length of the object.coefs minus the length of other, since this is just the vector here, if this is greater than or equal to 0 or else. So if this is greater than or equal to 0, object.coefs is going to be object.coefs plus. Now we will have some zeros, and exactly this amount of zeros, and other. So this is what I mean by that. So it seems like the object.coefs is long enough, and I want to prevent the following. If you are adding two vectors, if this one is 1, 2, for example, 3, but this one is basically 1 and 2, you cannot add them because the dimensions must agree. So what I do is I just look at the length of this one and the length of this one here, subtract them. So this is basically d here. If d is positive or equal to 0, then I can basically add them with padding the second one. So the addition should take place like this one here. So 0 should be prepend it here. Otherwise, I'm just going to do the exact opposite. So let's have object.coapps and then some zeros here. But the problem here now is, and you could maybe use an absolute value here. You can see that d is going to be negative here. I'm just going to provide a negative here, or you can just use absolute of d in order to prevent that from happening. Now, if this is the case, then we're basically done here. This would be basically the same. The only thing that will change is basically the way that I access other. It's going to be other.coapps because it's an object now, not a vector. So this is the only difference here, but the implementation stays the same. Here the data type of other is double. Here the data type of other is an object, Polynomial object, and we have a property called coapps. So I'm going to access that property as I'm doing it with this object here. Now, I'm just going to display the class of other and do nothing for now. So let's have polynomial 1, polynom, call it with 1, 2, 3. Let's have sims s, pol2, polynom, and then s square plus 4 for some reason. And I want to add pol1 plus pol2. There we go. So this is basically the result. Now you can see that res is actually another polynomial object. We can add objects to each other. So this plus was basically this plus operation, and it has its own definition here. So if you provide object and object, and if you provide another object here and check for the types, you can basically override this plus operation. By default, you're not able to add two things to each other if they're not numerical data. But you can see we can handle objects and override their behavior like the plus operation. We can override that, and we can treat them like polynomials now, because in mathematics we're able to add polynomials to each other. Why not in the programming language, in MATLAB? So this makes sense now, and we can add them to each other. Now, it is also interesting to note that I can even add another vector to it. Now I have overwritten the double here because I want to be able to add a double to it. Now, by default, I can still add a scalar to the polynomial because this is also a double, and it will just pad it with zeros, with according amount of zeros, and add it to the polynomial. The only problem would come up when we are trying to add, for example, a string. You can see there's a string. I did nothing about it, but that's basically it. If this would have meaning, I could also do something with that, but it does not. So I guess adding ASD will oh, nice. We can see that this is a character array, so we're not going to override that, so we are not messing up stuff here, because accidentally you might end up adding a string to a polynomial, but it shouldn't make sense. For these cases, we have assertion here, and we can just put that in and say cannot add polynom and then add maybe string and then class of other. There we go. Now we have also a nice message here. Clear CLC pol1 equals polynom So pol1 plus, I don't know, maybe char. You can see cannot add polynom and char. Now we have also a nice error message. We cannot add a string. What about true? We can add logical. There we go. Now we have prevented the additions that don't make sense, but it could be possible to add double or polynom. We could also extend it in terms of symbolic variables. We could say, okay, just add symbolic variables, but it would not be wise to do that, I guess, because it should be wrapped in a polynom class, so it will be converted into an object, and then you should maybe add them together. So, of course, we can repeat this whole thing here with minus. So let's do that quickly. And this will be called minus. And then we will have object, other, check if it's double. The only difference here is going to be this plus sign. Just subtract it, subtract that. Also this one here. And also this one here. There we go. And we should say subtract. There we go. Now we have basically plus and minus. What we can still do is we can implement other functions like integrate that integrates the current polynomial. Let's do that. So this is actually quite easy, and I'm again going to take the arithmetic root here. So integrate and then obj, and now this is not a special function, and it's returning value here. So yeah, we could take the arithmetic root, or we could also be lazy and just take sims s here, polynom equals 0, and then just copy this stuff here like this. I would then add this to Paul, but take the object.coefs times s to the power of that. So yeah, get rid of this. And then Paul integral is basically the integral of the polynomial here. And then value would be polynom poly. Of course, we're returning the integral as a new object. You could also maybe self-integrate it somehow. But what I mean by that is you might just take the coefficients of this and assign it to object.coefs so that it updates it, or you might want to store it somewhere else. So pol1, polynom. Let's have 1, 2, 3, and then pol1 dot integrate, and that's basically it. So of course we don't have this display function here. Maybe we can use that in order to see if it's working, but let's still move on. Let's also have differentiate here, which is again going to be basically the same like integrate. So let's call it differentiate, then object value sims, we just convert it into that. We might also have something like get sim or dot sim as a function so that we don't repeat this on and on, just have a function that returns a symbolic version of that and use that. That's also possible and maybe also helpful. So let's get that. Let's have diff and then Simar Pol, 1. Actually, we could also maybe pass an S here. We know what that is. So then the value would be Pol D here. So nothing fancy there. So now we have another function. And this one here is quite important because we want to check if the polynomials are equal to each other. And by equal, we mean equal by coefficient, if each coefficient is equal to the other one. Of course, we could also generalize this checking of being equal by just normalizing the polynomial in terms of the highest order here, because obviously they will share the root, but they will not be the same. But that's too much technical detail here. I'm just going to implement the being equal function here. You can extend it as you wish. This is just an example. So again, this equal is not a random function. It is a special one. And if this is double, then we have that again. We just check if it's equal to each other or actually not. So and I'm going to do it like the following. If this is not equal to this, and if the sum of this is 0, so I'm basically taking the same approach here. If 1, 2, 3 is not equal to 1, 1, 2, 4, or 5, you can see that the one that's not equal will give us a 1, and I'm going to check the sum for 0. I want this to be false for each coefficient. Therefore, I'm just checking it like that. Otherwise, it could be done with using the length here, but I don't like to use the length. So yeah, you could check if this is equal to length, then all of them are equal. But instead of doing that, I'm taking the inverse route where I'm checking if they're not equal, and if that's 0, then they are equal. So that's kind of the strategy here. So let's have something called vec here that stores this data. Vec, this is not equal to other, and then the same for here. Vec. This could be done cleaner, I guess, but yeah, since it's an example, I didn't really think about it. We might just look for other here, set that up, and then do the checking. Then we would check it once. There's always a better way of doing stuff here. But yeah, let's go with it. Cannot check if equal for polynomial and yeah, plus other. Here, once we've done that, the value, the sum of the vector should be 0. Nothing should be satisfied here. If that's the case, and then we should be good to go here. Yep. Now, let's have actually a more meaningful function, which is called plot, and then we will have display, and then we will talk about the whole class and how we have done it. So yeah, let's look at the plot function, because this is actually more exciting than anything else, I would say. So value, plot, and then object, and then end. So you might remember that when we are using plot, we give it t comma y, and then we have some properties, some extra properties, like line width, like display name, like color, and it goes on like that, like marker. We have lots of stuff to set up here. When you are in MATLAB, and if you are kind of writing a function that is a function about plot, you don't want to restrict the user to have the default colors, or you don't want to have some extra like color marker and stuff like that, it doesn't really make sense. A better way of handling it is using variable arguments in. And I'm going to show you how this is easier and more flexible than just coding it statically. Because plot itself uses this variable arguments in. This is a good example to show that here. So, yeah. If we want to plot a polynomial, most of the time we can do the following. We can check for its roots. If the polynomial has some real roots, that would be the x-axes. We would have x-axes there, and we should take them into account. So what I'm trying to do is here, I'm trying to come up with an algorithm that will automatically scale the x-axis and plot the polynomial so that we can see it basically. For that, I need the poles here, roots of object.coefs. So first of all, I get the poles. Now I need the minimum pole and the maximum pole. So the minimum of the real value of poles, also the maximum value here of that, and if for some reason we have min pole equals, if it's a perfect square, for example, if it's a if we have multiple points, so if this is equal to max pole, for example, s squared plus 2 times s plus 1, or in other words, s plus 1 squared. If this is the polynomial, then the maximum and the minimum will be equal, so I will have not a range here. So what I might do here is just to check if this is true. If that's the case, then min pole should be equal to -1, and then max pole should be equal to +1, because I have lost this could be done way better, I guess. We might have one +1 times max pole, something like that. But yeah, let's have -1 and 1, because I'm trying to come up with an interval here. So what is x, the minimum value x here? Well, I'm going to shift. Oh, okay. Now I'm going to shift it, min pole minus 0.5 times absolute value. This is not, this is just me doing stuff here, but you can just do it as you wish, how you wish it. I'm just having max pole plus, so yeah, that's basically it now. So we check for the roots. If they're not equal, we're just okay. But yeah, if they're not equal, then we take min pole, shift it a little bit, max pole, shift it a little bit with max pole, of course. And then we create an x vector here. That's all the thing. That's all we try to do here. Linspace, x min, x max, and like 100 points by default. So this is the x vector here. Of course, we have eval, and we might actually do this a little bit better here. So this eval function here does it element by elements. Well, yeah. We could somehow come up with a vector operation here, but I'm again not going to complicate it, overcomplicate it. You can do lots of stuff. So yeah, let's actually take this root here. Let's construct the polynomial here symbolically, and then let's have y weg, and then double, then substitute into the polynomial instead of s, xvec here. So that's basically what we're trying to do. So what did I do here? Well, I came up with, I looked at the poles of the polynomial. I took the minimum one, the maximum one. I have just ordered them. I shifted them to create an interval here, and I'm using that interval to plot it now. So I'm going to call plot xvec yvec, and then var arc in like this. So I'm just passing the whole stuff that will come after object, or that I'm going to provide here, into the plot function so that I can use it like the following. So this is a nice feature here. So let's define pol equals polynom, and then maybe 1, 2, 3, I don't know, and pol.plot. And what I can do here is quite the magic here. I can say the line width should be equal to 2. The color should be red. I didn't code this, as you can see. But once MATLAB is done, there we go. You can see I have basically the capability of adjusting stuff here remotely, basically. I don't care what the coloring, the styling here is. Plot has lots of styling going on. You can do everything. You can pass everything through the function so that we are basically just plotting the polynomial itself. We have used some algorithm to generate basically the x interval here. You might do figure 1 CLF, hold on, and then create this plot again. Yeah, we didn't grid on, so grid on like this, and then call the plot here. Then we have a nice plot here. So yeah, we can do whatever we want with this, but it is quite nice to have an object and then do stuff about it. We can maybe integrate it and then plot it. So let's have another polynomial, pol2 here, and then pol.integrate and pol2.plot, and then maybe the same here. So let me just call this one here. This one should be blue, and it should be pol2 plot. Now you can see, of course, the alignments are not there, but you get the idea. For some reason, I took the integral and I can plot it too. So we're treating polynomials like polynomials, and we can use MATLAB, and we can interface polynomials and say, okay, let's plot that. We might also have some checking here if, for example, the vararc in have some field names like, I don't know, x limit here. If we provide a certain x limit, then we use that x limit here, bypass this, so that we can match x-axes or y-axes for some reason. And yeah, that's basically the plot function. So let's have our last function display here. And you might be fed up with the whole polynomial stuff here. Let's change basically the example and then conclude our day. So let's have display object. So yeah, what we can do here is we can basically format our stuff a little bit. So I'm again going to use sims s. I'm again going to use kind of this part here, but not quite like that. So let me just paste it here and change it a little bit. So we have the order here. Instead of doing this stuff here, let's call it coef equals object.coefs I, and then Um, so if coef is positive, if coef is greater than 0, then I'm going to fprint f. So I'm just fprint f to print it with a plus sign, I guess, and then plus string coef times s to the power of n minus I plus 1. Well, but if I is greater than 1, makes more sense because this could be the first coefficient. If it's not the first coefficient, so let's shift it there. If this is the first coefficient, the plus sign doesn't make sense, but otherwise we might append a plus sign here because it's a positive thing, coefficient. Now, else if coef is equal to 0 with 1f, else and. If it's 0, I'm not going to do anything. Otherwise, we might have just a string here on its own. We don't need a plus sign here. And then maybe a printf new line. So why did I do this? Well, it's better to show than basically try to explain it. Well, let's have this polynomial here. And we did mess up. So let's see. If coefficient is positive, we don't need this pol here, never used it. If coef object at coefs I, if coef is positive, if I is greater than 1. Oh, this is not correct. This should be basically it. There we go. Now you can see it basically when we create it, and if we don't suppress the output with a semicolon, then if the class has something like display, this is again a special function like equal, like minus, like plus, you can see basically this is invoked on its own. So maybe we should have another new line to have a better formatting here. So that looks more like it. We could also have a tab here, I guess, in order to get one indentation here. So let's try that out. Maybe that looks better. Just a tab here. Yeah, this could be it basically. So we've created this here. Now, what happens if I have, for example, a minus sign here? You can see the minus sign is there. But if I wouldn't check if this is basically correct, then we would have a plus sign instead of this minus sign here. So that was the reason why we have that. So if this is basically 0, then we're skipping the S part here. You might also maybe display 0 here to indicate that that's also held as an information here. And now we can do stuff like the following. We can have polynom 1, 2, 3 minus polynom 1, 2, 3 and check if this whole thing here is equal to 0. Too many arguments, okay. Polynom 0, I guess. Oh, we have a missing parentheses here. And I guess we messed up a little bit. So why? It's not displaying the answer. What is the result of this? We still don't have an answer. results. Interesting. So what did we mess up here? Maybe we should do it like this, polynom 1, 2, 3. And then we have polynom 2, which is the same. Then polynom 1 minus polynom 2. We mess up stuff here. Interesting. Let's see. Minus, if this is a polynom and the other one is also a polynom. If it's 0, the difference is 0. Object coefs minus this. Okay, then, well, it should be equal to 0, I guess. Let's display object.coefs when we have a subtraction here. It's 0, 0, 0. It should be then the display part. Oh, yeah. Now the display part here displays nothing if we have 0 here, which was not something that I thought about. I guess we could do it a bit better than this. And I'm going full intuition here now. Let's have that. Let's actually go like this. Delete everything. And have that. So one indentation sims. I have the symbolic expression here. What happens if I say %s and string Paul? Hope that this does the job. Yeah, makes more sense. Okay. I quickly fix it now. Let's get rid of the minus object.coefs because the symbolic toolbox has a way of converting it to a string. This makes more and more sense now. So there was this result here. You can see it's 0. I can subtract like 1 out of it. We get s. And then we could just maybe check if this is 0 or polynom 0. Well, it still doesn't do what I thought it should. Because it should take the difference and then compare them. Maybe we should do it after it. Result equals 0. Yeah, didn't we have equal here? We have, if it's a double, it does some stuff. And then if this is equal to 0, oh. Now in equal, we kind of have the object here. That's the problem, okay. It should be val. All right. One more time. Is res equal to 0? Now it is. Now I can do this one here, or even this one here. So nice. Yeah, then we can plot stuff, we can integrate, we can check if it's 0. We also have if it's 0 or not. We didn't even bother to do that, so we can also say is 0. But oh, let's get rid of this part here. Still not doing it. We should first store it, I guess, and then check if it's 0. Is 0. There we go. Now, yeah, this is a very basic example, of course, because we're not fully utilizing the power of the object-oriented world. But what we have done is we have done the following. We have created an object, a class called Polynom, and it is storing some coefficients which we cannot see, which is isolated. But we've created ways to interact with this object, like create an object with a constructor here. We check if we have some arguments. If we don't have arguments, by definition, it should be 0. If we are providing an argument and if it's double, that should be the coefficient, the constant term. If it's a symbolic variable or expression, we're extracting the coefficients out of it and store it here. Otherwise, we don't have an idea on how to handle the value provided here. And we have ways of checking if this is a 0 polynomial. All coefficients should be equal to 0, and that's exactly what we're trying to evaluate here. We have a way of plugging in values where we have this eval function here. So we're just plugging in values into this polynomial, and we can add directly the objects, and we can subtract them. You can also have product and stuff like that. I didn't want to bother here, but you can have also product. And well, in the background, I'm just using these symbolic expressions because it comes at no price and it's so easy to do. But you might also want to do it natively without any symbolic assistance here. That's also possible. Maybe you have just one function that cares about that, and that should be the constructor, and maybe a get symbolic version out of it, and that's maybe it. You can add the objects to each other, which makes sense because polynomials can be added together to each other, or they can be subtracted from each other. We can integrate and differentiate, take the derivative respect to s, or integrate it respect to s, for example. We can check if they're equal polynomials. Of course, this is not a good implementation at this point. But yeah, you get the idea. You might extend upon it. I would say this is like the most important function of this object, because we can visualize the polynomial, and we can visualize different polynomials on top of each other with just one command. So when we have a user, the user can take this polynomial class, create a polynomial, and maybe do like something like 1, 2, 1. And once that's done, we can see what the polynomial is. And then, yeah, that was probably the reason why I used fprintf instead of converting it directly to a string, because the symbolic engine here does some weird ordering, which doesn't seem to be working all the time. We can have a line width of 2, and then maybe a color of red. And there we go, we have plotted our polynomial, as you can see here. So this is kind of the power that we're looking at, because you didn't adjust anything. We have just this polynomial. You can see it's true because it's 0 at -1. There are 2 basically poles here. And we have a nice visualization of the polynomial. We can also display it, and this display is invoked automatically. As you can see, when we're creating it, we're also seeing it. So this is also powerful. And we can extend upon this as much as we want. We can change the default parameter here. We can develop this into a more complex but handy tool to have basically capabilities here. So you might see the difference between a struct and this. This has more potential. You can embed functions and also maybe treat objects like they can be treated. This kind of capability is also available in C++, as far as I know. You can overload the operations operands here, like plus, minus, shift operator and stuff. That's also possible here in MATLAB. You can just check out the documentation for which overloading you can do and what it is basically meaning. So one of the ones that could be maybe useful is basically the power operator here. We could overload that so that we can take power. It would directly extend and update the coefficients here. That would be nice. We could convert it into a sim or get the symbolic version. So you get basically the idea here. So this is the first portion here. Now the second portion is more about the class um, in MATLAB or in general object-oriented programming. So let's create a class called shape. Let's call it shape.m class def. So there's also this class def MATLAB stuff here. Why didn't it work? We have some class attributes which I'm not going to go into detail for now. So yeah, that's basically it, the class here. So let's have properties. Is this helping me out? Properties. Yeah, it doesn't mean anything, but yeah. So let's have properties. And one of the property is going to be x because it's a shape. It can have a position. And let's have also vertices. So we kind of have a location x, y, and we are going to have vertices. So the cool thing about this is I can tell MATLAB that these are double values. But what I also can do, because we can also have vectors. Now, if you look at a class of a vector, it says also double. So saying double does not mean double in the sense of C++, that meaning that it's a scalar. It can be a vector in MATLAB. In order to prevent that, what we can do is we can just do 1, 1 here to indicate that this is going to be a scalar. A double scalar x and a double scalar y. And vertices is just vertices. We could restrict it to be double, of course, but that's basically it. Now, let's have also the methods here. Methods and then ends. Now, first we need a constructor here. Function and then object, because that will be created. Shape. And we're going to provide some x and y values. Now here we will assign objects x value to x, objects y value to y, and let's just say we don't have vertices, so let's have an empty vector. So let's add two more functions to it. Let's have a function called plot. And as you can see, I like to use object and var arg in. You can use it in a usual function too, in an ordinary function. You can do that, so that's not that big of a problem. So when we are going to plot it, we're going to use something called patch. And for patch, I'm going to show you how to do it. We need basically the size of object.vertices, comma 1, and then again 1. And then we need the vertices here. Patch vertices, object.vertices, faces, object.faces. Actually, we created local variable faces and then var arg in. All the arguments extra provided here should be here. Now, shape doesn't have actually a proper plot here, but I'm just creating it conceptually. Now, if you don't know what patch is basically a plot version, but it creates some shapes. You can look up the documentation here. It uses vertices and faces to kind of create the shape. Once we're done, you will probably see. So let's have another one, function print, object, and then name. I want to maybe save it. So print, and then name plus .png, dpng, and maybe a resolution of 150. So this on its own doesn't make much sense because this is not going to be the only object that I'm going to create. I'm actually going to create a triangle, for example. So we have a shape, and the class is called shape. It has members xy, denote the position, write a function that plots the shape, write a function that saves the shape as an image, etc., etc. Now let's create an actual shape, which is a triangle. So triangle dot m. So let's class def triangle. And what I want to do is I want to have some inheritance. Now, inheritance in object-oriented programming is the following. This is a shape. I can create a subclass that inherits stuff that I want it to inherit from shape, but has some extra capabilities or methods or functions or properties. So I don't want to repeat this over and over again. I will have something called shape. It will have a position, definitely. It will have some vertices, definitely. And if I create it, if it's a shape, generally I want to create it with x and y. But I want to have the capability of plotting it and printing it to an image. So plotting will basically be a default thing of a shape, because when you have a shape, you can place it somewhere. It's generic. I can plot it. I need to be able to print it to an image. That's what I'm trying to tell in this class definition. But here in triangle, I want to have an inheritance. It comes from shape, the class shape. And once I have done that, I can do the following. Let's have s equals shape. It takes some arguments. Let's have 1 by 2. You can see the shape has properties x1, y2, and vertices. So what happens if I create s2 as a triangle and give it a position 2 by 2? You can see it still works, but we didn't write any code in the triangle class here. So this is inheritance. All that is available in here will be available in triangle. I don't have to code it. I don't have to copy and paste it. And I can treat it like a shape, because triangle is a shape. It has its position, it has its vertices. Even though these vertices are not correct for the moment, we still have the capability of doing it. And I can just call s2.plot, for example. It does nothing, but yeah, I can do s2 print in order to save it. So you kind of have this tree structure where you have the shape, and triangle is kind of the child of the shape, has all the properties that shape has, but some of them will be changed and overwritten maybe. And that would be actually the function called constructor. The only thing that will change here is on how I will construct this here, because I need to have some vertices, for example. So let's, for example, call, of course, this is called triangle. So this is the constructor of my triangle. This is the constructor of the shape. If I want to still call all these, because I don't want to, again, explicitly tell that I'm going to set x and y, let's have edge, for example, another parameter here. So what I can do is I can say object at shape, which is going to call the constructor of shape. So this is copied and pasted just by calling this line. So it will take care of that. So basically, if I create a triangle, create a shape, and then I will do the following. So for example, I'm going to calculate the tip of the triangle. So that would be x1 is going to be x, y1 is going to be y plus edge divided by square root of 3. I guess that should be it.
left corner of triangle should be x2, which is x minus h divided by 2. And then y2 is equal to y minus h divided by 2 times square root of 3. Of course, the right corner then would be x3, which is x plus h divided by 2, and y plus, or actually y minus h divided by 2 square root 3. And then the vertices based on these will be the following. So x1 comma y1, and then x2 comma y2, and then x3 comma y3 here. Yeah, that should be it. Now, once we've done that, when we call plot, since we've created the vertices, we will see that this faces thing does the following. We have some vertices of a to the object. These are basically the list of vertices. And this is face 1, so this is vertex 1, vertex 2, vertex 3. And we tell the patch function here that from starting from vertex 1 up to the end and again to 1, that creates the face that we are going to plot here. So when we call this function here, let's try to call it now. Triangle, we need basically a position and then maybe an edge of 2. So you can see now we have s vertices here. And if I call s.plot like this, you can see we have a triangle. Now you can see that there's this position which is 2 by 2, and then I have like an edge of 2. So basically the length of this edge is 2. So what I can do, of course, is I can plot face color, call it blue, for example. And there we go. Now we have a blue triangle. Now, I didn't code to plot or how to plot basically the triangle. Basically, I know how to plot a shape. If it has some vertices, if it has a location, I can plot that. And basically the location is just set here, but not used here because during the creation of our triangle, we did basically this here. What we can still do is we can call a function called move maybe, and it will update based upon this position. And yeah, then we can basically also move the object. But the whole idea is that we can have a shape class and we can implement a subclass based on the shape class. We can call the constructor here to not repeat code, and if there's a hierarchy between your objects due to its nature, like in this example, then you can just also use this inheritance property of object-oriented programming. So we can also go ahead and repeat this stuff for basically a rectangle here. Rectangle.m, call it rectangle. There we go. This also inherits that shape, all the properties of shape. The only thing is that the creation will change. Now we need a width and height for it. You can see that the way of creating objects changes, but we still call the superclass, so it is called constructor here. So the first edge is going to be x1 is going to be x minus width divided by 2. And y is going to be y minus height divided by 2. Yeah, it's going to be basically going like this. So let me get rid of that. So x2, y2 is going to be, I guess this one should be plus, or this one here. So then, if I'm not mistaken, we should basically have 3, 3, 4, 4, and this should be plus, plus, and then this should be minus, plus. Hope that I didn't mess it up. 4 and 4. And there we go. Now we can also have s equals rectangle, like 4, 4, 2, 1. S dot plot. There we go. Now we have a rectangle at this specific position with width and height defined by that. Now what we can do is, of course, we can go ahead and save this whole thing into a PNG file. So s.print, let's call it a name, I don't know, result. There we go. Of course, this is the capability of shape. And this doesn't mean that we will just get the triangle or the rectangle, but you might do that when you just clear the figure somewhere here and call the plot internally and then print maybe. Or when you plot it, you can just clear everything else and then just export the triangle on its own. But you can see that we can have a superclass, a class that has the generic description of our class, and then we can have some variations on that to have a rectangle, to have a triangle. And the nice thing about this is that we are creating some portion of the data differently, but if we have a pipeline, a renderer, then we can view all these as shapes. So basically, a shape has a plot and a print function, and for example, the renderer only cares about plot. It can just call the plot function and we're good to go. Now, I hope that this was helpful to introduce you to the object-oriented world. It's an advanced topic, of course, because of the fact that you first need to have basic MATLAB knowledge, and then you have to be be familiar with encapsulation and stuff like that. And if you have the need for it, then this is quite useful and important. You can see we have developed a class which is not even complete at all, but it has some nice capabilities. We can do stuff like interesting stuff like given here as an example. Hope that this was helpful and see you in the next videos.